If you've ever looked at a design document, maybe a UML class diagram with all those clean boxes and just thought, how do I turn this logical structure into actual working Python code?
Hmm.
Then this deep dive is absolutely for you. We're not just talking about the basics of defining a class. We're really getting into the architectural side of things. How Python handles attributes, why its access control is so different, and how that all feeds into some pretty advanced design patterns.
That's exactly it. The source material we're looking at today is, well, it's a complete roadmap. We're moving past just definitions. We want to understand why Python has these conventions. We'll cover everything from, the basic class syntax and initialization, all the way to the big differences between instance, class, and static methods. And then, yeah, we'll get into the fun stuff like the singleton and manager patterns.
Okay, let's unpack that, starting right at the beginning with the vocabulary. Because in OOP, you hear class and object thrown around all the time, sometimes like they're the same thing. But they're really not, are they? Oh, not at all. And that distinction is fundamental. Think of the class as the blueprint. It's the schema, the mold. Architecturally, a class is just a user-defined type. The name you give it, say, car. That's now a new data type in your program.
And the object is what you build from that blueprint.
Precisely. The object is the instance that you create or instantiate from that class type. You're always defining a type first, and then you make many instances or objects of that type.
Right. So moving on to the actual mechanics, defining that blueprint in Python's pretty simple. You just use the class keyword. But the sources really emphasize sticking to the PTP8 naming convention, which is cap words.
Yeah, cap words, or some people call it Pascal case, means capitalizing the first letter of each word, like HTTP request manager. And it's not just for looks, it's a signal. It tells any other Python developer, hey, this is a class, it's all about clarity.
But this is where Python's famous flexibility kind of creates a problem, doesn't it? I'm talking about attributes. Exactly. In Python, you can just add an attribute to an object whenever you want. You just use the dot operator dash myObject dot new attribute equals hello. And while that might seem useful, for consistency, it's a total nightmare.
Because if only some of your user objects have a last login attribute, how can any other part of your code possibly rely on it?
It can't. And this is especially painful for tools designed to help us, the static type checkers.
Like MyPy.
Exactly like MyPy. These tools analyze your code without running it. If attributes just appear out of nowhere, MyPy has no idea what's going on. It can't help you find bugs.
So if adding attributes dynamically is the problem, then initialization has to be the answer. That's how we get consistency.
It is. Now, a lot of other OOP languages have a true constructor. Python does have one. It's the new method.
Yeah.
But you almost never touch that. Not unless you're doing something really advanced, like that singleton pattern we'll get to later.
So we use the initializer instead.
Yes. The common practice, the day-to-day work, is done in the init method. Its only job is to set up all the required attributes for an instance. It guarantees that every single user object you create will have an id and an email every single time. Consistency.
Okay, so once we have our data, our attributes, we need behavior, we need methods. And here we hit a core Python rule. Every method inside a class needs that first parameter, self.
That is the crucial part. Self is basically a pointer to the instance itself. If you have user and user, you call user.change password, the user object is what gets passed into that self parameter.
Now, the sources make a big deal about self being a convention, not a keyword like this in Java. Does that really change anything from an architectural standpoint?
It matters a lot, actually, because it speaks to Python's whole philosophy. In Java, this is a keyword. The compiler controls it. In Python, you could call it something else, but you never should. Sticking to self is all about readability. But architecturally, because it's not a keyword, it allows for more advanced reflective programming. But yeah, for 99% of code, just use self.
And while we're talking about parameters, we should probably mention type hints and default values too.
Oh, absolutely. Using type hints, like saying a parameter x is an int, is just essential if you want tools like MyPy to be effective. And default values just make your methods easier to use. It's all part of building robust, easy-to-understand code.
Let's shift gears and tackle maybe the biggest difference between Python and other OOP languages, access control. In languages like Java or C++E, you have keywords like private and public. Python just doesn't do that.
Nope. It operates on this principle of we're all adults here. The language designers trusted that if a developer knows they shouldn't touch an internal variable, they just won't. It's a system built on trust and convention, not the compiler forcing your hand.
So if there are no keywords, how do we signal that something is supposed to be internal? It comes down to underscores, right?
It's all about the underscores. Let's start with the single leading underscore, like internal cache. That's Python's gentle hint. It says, hey, this is for internal use. You probably shouldn't mess with it directly. It's a notion of privacy. But you can still access it if you really want to. That's an honor system.
And then there's the more aggressive version, the double leading underscore, like secret key.
Right. The double underscore is a much stronger demand for privacy. What Python does here is something called name mangling. It secretly changes the name of the attribute. It adds the class name to the front, so secret key becomes something like class name secret key.
Which makes it harder to access from outside.
Much harder. But here's the key point. It's still not enforced. It's a naming trick, a convention. If you know the mangled name, you can still get to it.
So if direct access is discouraged but not forbidden, what's the professional way to expose data but still have control over it?
That's the perfect question, and the answer is the @property decorator. The best practice is to always store your data in an attribute with a leading underscore, like temperature. Then you use methods to create a public API for getting and setting that data.
And @property is great because it makes a method call look like you're just accessing an attribute.
It's brilliant. You can have a whole bunch of logic, validation, whatever, inside your getter method. But to the person using your object, they just write thermostat.temperature. It's clean.
I love that. It gives the user simplicity while the developer keeps all the control.
And that control extends to changing the data, too. You can define a setter using a method name.setter. That setter is your gatekeeper. Before it updates the internal temperature, you can check if the value is valid. You can even define a deleter. This whole pattern private storage with a controlled public property API is how you do encapsulation the Python way.
Okay, let's talk more about methods. We know what an instance method is, but the sources break them down into 3 distinct types, and it all depends on what kind of state the method needs to access.
Exactly. So the first and most common is the instance method. That's the one we've been talking about.
The one that takes self.
The one that takes self. It's tied to one specific object. It has full power to access and change the attributes of that specific object. It manages the object's state.
Got it. So next we move up a level to class methods.
Right. And you mark these with the @class method decorator. The huge difference is they take CLs as their first parameter, not self. The CL's parameter points to the class itself, the blueprint.
So it can't touch instance data.
It can't. It can only access or modify things that belong to the class as a whole, variables that are shared across all instances. You often see them used as like alternative ways to construct an object, but they're limited to the class level.
And that brings us to the third type, the most isolated one, the static method.
The static method is marked with @static method, and it takes nothing, no self, no CLs. It's basically a normal function that you've decided to stick inside a class's namespace, probably for organization.
Right.
It can't change the object state, and it can't change the class's state. It's just a utility function that's logically related to the class.
So the rule of thumb is use an instance method if you need to work with this object's data. Use a class method if you need to work with something shared by all objects of this type.
Right.
And use a static method if you just need a helper function that doesn't rely on any state at all.
That's the perfect summary of the architectural distinction. And here's where it gets really interesting. We can now move from just the mechanics to, full-blown architectural patterns. Let's talk about the Singleton pattern.
Okay, the Singleton. The basic idea sounds simple enough. You want to make sure there is one and only one instance of a class in your entire program. Why would you want to do that?
It's usually for managing some kind of unique global resource. Think about a database connection pool or a configuration manager or a logging service. You only want one of those things, otherwise you get chaos and conflicts.
Now, we mentioned that in other languages you do this by making the constructor private, but the sources also say that the Singleton is sometimes called an anti-pattern. Why is it so controversial?
It's an anti-pattern, or at least can be, because it creates hidden global state. It creates tight coupling. If 20 different parts of your code all depend on this one global instance, it becomes really hard to test those parts in isolation. You can't easily swap in a fake object for testing.
And since Python doesn't have private constructors, trying to build one manually using that new method seems like you're fighting against the language.
You really are. You could do it with new, and it's a clever trick, but it's often overly complicated for what you need in Python. We should really lean into the more Pythonic, simpler ways to get the same result.
And the sources gave two really elegant alternatives. The first is to just use a Python module.
This is the genius built-in solution. When you import myconfig, Python runs the code and creates a single instance of that module. And every single time you import that module again, anywhere in your code, Python just gives you back that exact same instance. Python modules are, by their very nature, singletons. It's perfect for configuration.
That's amazing. We use this pattern every day without even thinking about it. What was the second option?
The second way is to just use a normal class, but design it so it doesn't depend on instance state. You use class-level attributes and a lot of add static method decorators. If your methods don't need self, then you've essentially made a namespace for data in functions, which has the same effect as a singleton.
That makes sense. Building on that, let's talk about the manager object, the thing that ties all these pieces together.
Yes, manager objects. They're a key architectural piece. They sit at a higher level and act as the orchestrator. They don't usually do the heavy lifting themselves. Instead, their job is to manage and assemble other, more specialized objects. Their main job is delegation. They pass messages and tasks around to the objects that actually do the work.
So if I have a payment processor and an inventory system, the order manager is the object that makes sure they talk to each other correctly.
Exactly. The order manager is the air traffic controller. And because of that, they're often linked to another pattern, the facade pattern. They present this simple, easy-to-use surface of facade that hides all the complexity of the subsystems working underneath.
And they could also act as an adapter, right? Helping different components communicate even if they weren't designed to.
Absolutely. The solution or main class in a big project is very often a manager class. And because you only want one central orchestrator, manager classes very often use the singleton pattern. It ensures there's only one of them. See how it all ties together? The consistency, the access control, the patterns. It all builds up to these high-level architectural roles.
So what does this all mean for you as you're learning this? We've gone from why you should use cap words for a class name all the way to orchestrating a whole system with a manager.
I'd say there are two huge takeaways. First, Python's OOP is built on convention and trust. That system of using underscores for access control and then using it properly to create safe public APIs. That is fundamental to writing good Pythonic code.
And second, really understanding the roles of the three method types, knowing when you need self, when you need sylls, and when you need neither. That decision directly impacts how clean and testable your code is. These concepts are really the foundation.
They are. And the source material is clear that when you apply these ideas, your code quality just goes up. You enable tools like MyPy to help you, you make your code easier to document, and you prevent a whole class of bugs before they even happen.
Which leads us to a final provocative thought for you to take away from this. When you start a complex new project, say you're building a system to model a financial portfolio, you have to make some hard design choices right at the start.
And here's the specific challenge. As you design your main classes, how do you decide what data must be defined in init as part of the core essential state of the object versus what data is calculated or transient or sensitive and should be hidden away as a protected attribute exposed only through a safe getter method? That distinction between core state and a calculated interface, that's really the key to mastering object-oriented design in Python.